Hello. In today's class, we are going to discuss the dielectric constant and polarizability. The dielectric constant of a isotropic or cubic medium epsilon r is given by epsilon 0 e plus p, the polarization vector p divided by epsilon 0 e. Okay. So this is the expression on the relative permittivity or dielectric constant, which is given by epsilon is also given by epsilon 0. It is the ratio of the permittivity of the medium to the permittivity of free space. Okay. So this can also be written as, so epsilon 0 e divided by epsilon 0 e is 1 plus p divided by epsilon 0 is equal to chi. So epsilon r is equal to 1 plus chi or 1 plus chi e, the dielectric susceptibility. Okay. So this is equal to epsilon divided by epsilon 0. Okay. So from this expression we can write this thing as epsilon 0 epsilon r is equal to epsilon, or epsilon 0 epsilon r e equal to epsilon into a. This is equal to d, the displacement vector. Okay. So epsilon, the displacement vector d is equal to, this is equal to epsilon 0 e plus p. Okay. So we got this expression. Here we have epsilon r is equal to 1 plus epsilon r is equal to 1 plus chi, where the electric susceptibility is equal to p by epsilon 0 e. Okay. So for a cubic medium, for cubic material, the polarization vector p is equal to epsilon 0 chi times E, the macroscopic field macroscopic electric field E. For a non-cubic or anisotropic medium, okay, non-cubic medium, then polarization as components px, py, pz is given by p mu is equal to epsilon 0 chi mu nu into E nu. According to Einstein convention, summation convention, Px is equal to epsilon 0 chi xx Ex plus chi xy Ey plus chi xz Ez, and py also, py is equal to epsilon 0 this can be expressed as so this is the susceptibility tensor chi mu nu. So we can write, therefore we can write therefore we have p mu is equal to epsilon 0 chi mu nu E nu. Okay. Similarly, the dielectric constant tensor epsilon r mu nu is equal to delta mu nu plus chi mu nu. This is the dielectric constant tensor. Epsilon r mu nu is equal to delta mu nu plus chi mu nu. Here delta is the delta mu nu is equal to 1 if mu equal to nu is 0 when mu not equal to nu. Okay. Now we know that the dipole moment of an atom P is directly proportional to the electric field at the atom or the local electric field, or we can write P is equal to some constant alpha into local electric field. Okay, so the dipole moment of an atom, if the atom is neutral, if an electric field is applied, there will be a particular electric field at the atomic site, so that is called the local electric field. So this local electric field determines the dipole moment of the atom. Here alpha is called the polarizability of the atom. Alpha is the polarizability of the atom. So polarizability of the atom is described in terms of the local electric field, which is expressed in this form: P is equal to alpha E local. We know that polarization vector P is the net dipole moment per unit volume, or we can write in this is equal to summation Nj Pj. Okay, if Pj is the dipole moment of jth atom and if Nj is the number of dipoles or number of atoms per unit volume at jth atom, near jth atom, Nj is the total number of atoms per unit volume, then the total dipole moment per unit volume is given by summation Nj Pj. Okay, Pj is the dipole moment of a particular atom, jth atom. You can use the above expression for Pj. So this is equal to summation Nj alpha j E local, E local, okay, E local of jth atom. So if we sum over all these j values, then we'll get the total dipole moment per unit volume, which is the polarization vector P. Here P is the bulk property. P means the polarization vector of the crystal, whereas this alpha j is the polarizability of an atom, and E local is the electric field at the atomic site. But we know that the local electric field is given by this expression, the macroscopic field plus P by 3 epsilon 0. Okay, so this is the expression of the local electric field at an atomic site. So therefore the equation of the polarization vector P becomes summation Nj alpha j into E plus P by 3 epsilon 0. Okay, for all j. So taking P to one side, P into 1 minus summation Nj alpha j divided by 3 epsilon 0, which is equal to summation Nj alpha j into E, or the polarization vector P is equal to summation Nj alpha j E divided by 1 minus summation Nj alpha j divided by 3 epsilon 0. But the susceptibility chi is equal to the polarization vector P divided by epsilon 0 E. Okay, which is equal to, so substituting the value of P, substituting the expression for P here, summation Nj alpha j into the macroscopic field E divided by 1 minus summation Nj alpha G divided by 3 epsilon 0 divided by epsilon 0 into E. Okay, so this E and E get cancelled, so therefore this can be written as, so this is chi. Chi is equal to epsilon r minus 1. So we have seen epsilon r is equal to 1 plus chi, or chi equal to epsilon r minus 1. So susceptibility can be written in this form. And therefore epsilon r, so this is equation number 1. Now epsilon r plus 2. So I have added 3 with this thing. So epsilon r plus 2 is equal to 1 by epsilon 0 summation Nj alpha j divided by 1 minus summation Nj alpha j divided by 3 epsilon 0 plus 3. This is equal to 1 by epsilon 0. So taking 1 minus summation Nj alpha j divided by 3 epsilon 0 as LCM. So this 1 minus summation Nj alpha j divided by 3 epsilon 0. Here is Nj alpha j plus 3 times 1 minus summation Nj alpha j divided by 3 epsilon 0 into epsilon 0. Therefore this is equal to 3 divided by 1 minus summation Nj alpha j divided by 3 epsilon 0. So this is epsilon r plus 2. So we have expression for epsilon r minus 1 as well as epsilon r plus 2. So dividing epsilon r minus 1 with the epsilon r plus 2, we get, so here 1 minus summation Nj alpha j divided by 3 epsilon 0 is there. Here also same quantity is there. So therefore if we divide this thing, we will get, this is equal to summation Nj alpha j divided by 3 epsilon 0. So here epsilon r is the relative permittivity or the dielectric constant, which is the bulk property, the property of the crystal, and alpha j is the atomic property. So this expression relates the atomic property and the bulk properties. Okay, and this equation is called the Clausius Mossotti relation. Now let us talk more about the polarizability. We know that when an electric field is applied to a crystal, there will be charge separation. So negative and positive charges will be separated when an electric field is applied. Therefore, there will be dipole moments for an atom. You know the dipole moment is P is equal to alpha E local. Okay. So this alpha is the polarizability. This polarizability can be separated into 3 parts actually. Okay. So alpha total can be separated into, alpha is equal to 3 contribution, that is alpha E plus alpha I. This is alpha E electronic polarizability, alpha I is ionic polarizability, and alpha dipolar. Okay. Or alpha O. in some text alpha O also. Alpha O means orientational polarizability. So these are the three contributions of the polarizability, total polarizability in this equation. So the electronic polarizability alpha E is due to the separation of electron charges or electron shells from the nucleus. So when an electric field is applied, there can be a change of electron charge, the shifting of electron charges with respect to the nucleus. So this causes the electronic polarizability. Similarly, ions, a particular ion can be separated from the other ion, a cluster of ions from a group of ions, one ion can be separated. Okay, so this causes the ionic polarizability. And there can be dipolar polarizability, that is, for a permanent dipole, if the material is polar material or there will be permanent dipoles, then orientation of the dipole changes with the electric field. So due to this there will be a polarizability, so that is called dipolar polarizability. So electronic polarizability due to separation of electron charges, electron shells, you can say that, electron shells from the nucleus of the atom. Then ionic polarizability arises due to the separation of an ion from other ions. Okay. Then alpha dipolar or alpha O, orientation polarizability. It is due to orientation of permanent dipoles in an electric field. Okay. So these are the three contributions. The electric field applied to the crystal may be in the form of electromagnetic waves. So electromagnetic wave these waves have high frequency. So in the optical frequency region, that means the frequency in the range of 10 raised to 14 to 10 raised to 15 hertz. So the contribution of ionic and dipolar polarizability is very negligible in optical frequencies because of their masses. Okay, so they are massive compared to electrons. Dipolar polarizability is for molecules, because for permanent dipole moment is only for molecules. For atoms, permanent dipole moment is 0. So because of their masses, that means because masses of ions and molecules are very much greater than electron masses. So at optical frequencies, the only contribution is the electronic polarizability. Okay. So at optical frequencies, then alpha is equal to alpha E, because alpha I plus alpha dipolar can be neglected, okay, in this equation. So because of their inertia of these ions and molecules. So therefore the only contribution is electronic polarizability only in the optical and higher frequencies. Optical frequency means the frequency for X-rays, for gamma rays also, this is the case. Okay. In this expression. Therefore, at optical frequency, epsilon r is equal to n square. N is the refractive index of the electromagnetic wave in that medium. Okay. So epsilon r is equal to n square. Therefore, we can write the Clausius Mossotti relation in this form: n square minus 1 divided by n square plus 2 is equal to summation nj alpha j divided by 3 epsilon 0. Okay. So the Clausius Mossotti relation can be rewritten in this form in terms of refractive index for optical frequencies. Here alpha j is the electronic polarizability of the atom. Next we can talk about the electronic polarizability in detail. In a free atom, the charge distribution is such that the net dipole moment in the absence of an electric field is 0, or the dipole moment of the atom is 0 when there is no electric field. Therefore, the center of gravity of the electron coincides with the nucleus. The center of gravity of the electron charge distribution coincides with the nucleus. So, therefore, there is no dipole moment. Now, consider an electric field E is applied. Then this electric field takes the electron distribution away from the nucleus. And at the same time, the attractive force between the electrons and the nucleus will tend to bring back the electrons to the original state. So, there will be a balance between these two. So, an equilibrium state is reached in which there will be a finite dipole moment. Okay. So, what are the things? First one. So at equilibrium, these two forces balances and there will be a finite dipole moment. To find out the magnitude of the electronic polarizability, let us consider the following model. Suppose the atom is represented by a nucleus of charge Ze, where Z is the atomic number, and a negative charge distribution inside the sphere of radius r. Okay, so a negative charge distribution is having a radius r, and there is a nucleus of charge Ze, the center. If an electric field is applied, this nucleus charge from the electron charge distribution will be separated over a distance small d. Okay, so this is shifted to a distance. Ze is shifted by this magnitude. This electron distribution will pull this nucleus back to the original configuration. So therefore, at equilibrium, the electrostatic force on the nucleus Ze times E in the electric field is balanced by the electrostatic force between the electron charge distribution, that is 1 by 4 pi epsilon 0. Ze is the charge of nucleus into charge of electron distribution shifted as rho into V volume shifted divided by the distance square d square. Okay, so this here rho is the density of electron distribution. So 4 by so this is electron charge, total electron charge is Ze divided by volume is 4 by 3 pi r cube, where r cube is the radius of electron charge distribution. So this is the density, and the volume shifted is equal to 4 by 3 pi d cube. Okay. So substituting all this here, we will get 1 by 4 pi epsilon 0 Ze into Ze divided by 4 by 3 pi r cube into 4 by 3 by d cube divided by d square. So on simplifying, we get Therefore, E is equal to 1 by 4 pi epsilon 0 Z E d divided by r cube. Okay. But we know that the dipole moment, induced dipole moment P is equal to the charge Z E into d. Okay. This is equal to Z E d from this expression is 4 pi epsilon 0 r cube times E. So the dipole moment P is equal to 4 pi epsilon 0 r cube E. But we know the dipole moment P is equal to alpha E. Okay. So this electronic polarizability alpha E times E. Comparing these two equation, we get alpha E is equal to 4 pi epsilon 0 r cube. This is the expression for the electronic polarizability. Here R is the radius of the atom or radius of the electron charge distribution. Okay. So this is in SI unit. In CGS unit, this is alpha E is simply R cube. In CGS, alpha E is equal to R cube. This 4 pi epsilon 0 will become 1 in CGS unit. Okay, so this is about the electronic polarizability. So today we have discussed what is dielectric constant and what is polarizability, the relation between the dielectric constant and the polarizability, Clausius Mossotti relation we have derived. Then we have discussed what are the different contributions of polarizability. They are electronic polarizability, ionic polarizability, and dipolar polarizability. So if the electric field applied is in the form of electromagnetic waves in optical frequencies, the Clausius Mossotti relation is rewritten in terms of refractive index of the crystal. Then we have seen what is electronic polarizability. The electronic polarizability equation is also derived. That's all for today.